Alright, hello, welcome back. Um, Basically done with the binary adder now. Although there is one last thing to do. Just this one small thing and then it'll be done, at least for the time being. That should shut that off, which means that can only be on when that's on, which is what I want. Yes. Anyway, so that's the binary adder done, for the time being at least. Which means I now need to move on to binary comparators. Well, I could do binary comparison, or I could do multiplication, or I could do 2's complement subtraction, or I could do division. But binary comparators is easy, so I'm going to do that now. Well, I'm not going to do that now. I'm going to start doing that now. You know, it'll take me a few weeks, I guess, but well, it'll probably only take 2 or 3 streams, so a couple of hours to be honest. But like building that only took about 3 days, 3 streams really, and it's going to be simpler than that. But then I'm in a low energy mode right now, so you know what? Why don't I copy the base from that? Yeah, I'm in a low energy mode right now, so it's going to be difficult and slow progress for a few weeks, but heck, it might be difficult and slow progress all summer, but we'll see, we'll see. Oh, excuse me. There we go. That's an interesting profile. Also, it doesn't help that I'm currently in a pretty severe fast. Lost. Yeah. For sporting reasons, I put on a lot of weight in the winter, and then in spring I have to fast it all off, which is a bit brutal, but it's good for the metabolism, I guess. I mean, I don't guess, I know, but either way, I'm low energy, and that's the point of this little conversation. So if I don't get too much done, that's partly why. You know what? I'm going to do the whole torches around the outside edge. I really should just set it to daytime permanently. Probably going to fill this exactly in with red wool again later, but for now I want a blank slate and I also want to procrastinate. To be fair, I probably should have done this actual playing Minecraft stuff off stream. Then I could just do the logic circuits on stream. But hey. I figured out a system for the binary comparison that should be very simple and easy to put together, so I've also figured out a system for binary multiplication that should be decidedly less simple to put together. So that's why I'm doing binary comparison right now. And yes, part of the point of this is that it's partly a challenge, right? So part of it is that I have to figure this out for myself. You know, I'm trying not to I'm trying not to research how real computers work as much as possible. I'm also trying not to research how Minecraft computers work as much as possible. Although I do have a little bit of past knowledge of computers, so it's not a 100% clean run. And by past knowledge of computers, I mean past knowledge of like logic circuitry, like logic gates and that crap, right? It's like I have extensive prior experience of programming, so it's like, you know, I'm very familiar with computers, you know, but I'm not super familiar with how they work on a chip level, basically. Which is the point of this, right? The point of this is to figure out how computers work on a hardware level, as opposed to just knowing software. But as an extra challenge, I've got to figure it out for myself rather than just mimicking what's already been done. I don't know why I'm bothering, so I'm just going to fill this in with moss again in a second, so it's a bit pointless, but I suppose I like a clean slate to work on. Also, binary comparison is going to be a significantly simpler device than binary addition. See the RAM out the back there. Again, just a tiny corner of the RAM you can see there. But I'm really pleased with that. Like, the RAM is such a neat structure. It's relaxing to play a bit of Minecraft every now and then. Take a break from the circuits and just dig and build. So binary comparison is going to be a very simple series of switches. What I'm going to do is I'm essentially going to check. So to know if a number is bigger than another number, right, in binary, if I've got this correct, all I need to do is, well, let's imagine both the numbers are the same, right? Then we know that each number has the same binary pattern, and therefore, well, that's the null case, right? In the non-null case, a number is different, which means that there's guaranteed to be one bit that is a 1 in one of the numbers that is not a 1 in one of the other numbers. Right, because the numbers are different, so there's going to be at least one difference. And to know which number is the largest number, right, all we need to do is find the highest order bit for which that is the case, right? So the highest order, the number with the bit, with the highest order unique bit, right, or non-shared bit rather, non-shared 1 rather, not bit, because obviously they both have 16 bits. It's whether or not it's on or off that matters. So the number with the highest order unique 1 is the larger number. So all I need to do is find that highest order unique 1. And I've got a fairly simple system for doing that, which should work fine. And also, right, because comparison can either be greater than or less than, or it can be equal to, right? So this comparator will return one of three. It will either return greater than, well, return one of, so it will return true or false to the statement of is this number less than the other number, right? And then it will also return null for the numbers of the two numbers of the same value, which means that will cover greater than or equal. It will recover greater than or less than, and it will also recover equal to. What it will then do is it will send that number to a local. This is something that actual computers do, I think. or at least I was reading the specifications for my GPU the other day, and apparently they have essentially they have a bit on the like near the processing unit that stores the value of any recent logical comparison operations, so that basically the code can have fast access to it, um, rather than sending it to memory, for example. They basically just have a local true or false state storage system that read from very quickly. But that's what I'm going to do here, right? I'm going to have basically the comparison is going to output its result to something that will be separate from the main memory system, and it will be accessible by if else state by if statements, right? So we're not going to have in operator code, right? We're not going to have if statements, and I have goto statements and conditional goto statements, and that will allow for loops and if statements. A goto statement is basically just a statement that says go to this line of code, but in this case, each line of code is a memory address, right? So instead of going to this line of code, it will say go to this memory address and read the code there. So that allows, for example, to loop back to a previous memory address, to a previous line of code that corresponds with the previous memory address, for example, and that will allow you to do a loop, or it will allow you to skip over a block of code conditionally, which would be an if statement, right? So basically the binary results of this are going to be sent to a separate register, which will be read by an if statement, well, not an if statement, conditional goto statement, not statement, operator. Although there does need to be access to that also to send it to memory, because you need to be able to send Boolean results to memory. So it's not going to be entirely separated, it's just going to be logically separated. Goodness, I'm clanging a lot today. Also, I've thought about it, and I think I am going to have to add an extra bit of memory of operator space. So currently it's using 4-bit operator codes, right, which gives me 16 operators. But I think I'll need more than 16 operators, because just these mathematical operations are going to take six operations, right, and then it's going to be hardly any left. So it's likely that I'll have to go to a 5-bit operator code, and because of the way I've set up the architecture, that will mean going from a 12-bit memory address space to an 11-bit memory address station. Oh god, my tongue. Sorry, excuse me, I'm just not speaking good. 11-bit memory address space, right? And yes, I appreciate that 5 and 11 is non-multiples of 2 is horrible. But you know, it might need to be done. But yes, it because of my architecture, right, I've got I've got basically the way I want the code to be is I want the memory. I want in a memory address space over there, right, which is 16 bits. So it's got 2 bytes per memory address, and in that 2 byte bit, I want to have the operator code and the address space that it points to, that's associated with it, right? So it can send an operator code and a memory address to the CPU simultaneously, right? Which basically saves one read from the RAM to the CPU every time I want to do a command, right? Because it's not reading a operator code and then an associated memory address. It's reading the operator code and the memory address simultaneously. So I can say perform operation X on address Y, right? And I can store that information in one 16-bit address. But what that does mean is I've got to split the operator code plus the memory address can't be greater than 16 bits, right? Obviously, first logical separation is 4 and 12, which is what it's currently doing, right? 4-bit operator code with a 12-bit memory address in a 16-bit system. But again, it's looking like 4 bits of operator code space, so 16 possible operators is not going to be enough. So I'm going to have to go to a rather horrible 5 and 11. Which it'll only be a very, very small modification, right? Very simple and easy to do, but heinous and ugly in computer science terms. Anyway, I'll cross that bridge much later because I'm gonna have to build the first 16 operators before I even get there. I mean, I guess I've done the first operator, which is binary addition. And this will be the second operator, binary comparison. And that's good. So, and now time to replace this all back with moss. You'll see it's actually got a much smaller footprint than the binary adder. The binary adder required XOR gates, right? And XOR gates are ridiculously complicated to build. This just requires a couple of switches. So imagine two 16-bit numbers. It needs to be a bit wider, doesn't it? So this is the ground layer, which is the 0th order layer of each of your two 16-bit numbers that you're comparing. And basically you want... that's interesting, actually. just occurs to me that it's not quite as simple because topologically it can't be done in a 2D plane. Topologically it needs to be done in a 3D plane, which is similar to the XOR gate. It's still much more simple than an XOR gate because it's just still just two switches. But also if I just use an AND, essentially, right, all I need is if this side is on, right, I need it to switch that side off, and if this side is on, I need it to switch this side off, right. And then obviously if both sides are on, that means I'll get 0, 0 out, right, and if one side is on and the other side is off, I'll get 1 out. Well, actually, I know how I can do this in the 2D plane. All I need to do is put an AND gate in the middle, and then that will be fine, basically. I put an AND gate in the middle, then switch it with that AND gate. Like so. Swap passes for an AND gate around here. So just going to put the connector pins on. So it looks a bit like a connector pin. Anyway, that's an AND gate, I believe. Yes, so if this side's on, that switches that off, which allows that to go through, which is an AND gate, yes. I can make it a little smaller. Like that. That's the AND gate, and then add another layer or two here. So, and then this comes over here, switches that off. Now you can see that side's on, that side's off. Get a 1 out. That side's on, that side's off, we get a 1 out. They're both on, we get 0 out. Right. And what? That's the first half of the binary comparison, right? Obviously I will need a stack of 16 of these on top of each other, right? And what that will do is that any number that doesn't any bit that doesn't match its corresponding bit in the other number will result in a 1 being returned on either its side, right? So it'll be, if it's this number, it'll be returned on that side, and if it's that number, it'll be returned on that side. Which is where the second mechanism comes in. This is where the magic happens, and it's a little bit more complicated. So it's going to involve a downwards propagating redstone signal. So, oh, goodness. So the only problem here is this is going to add an enormous amount of latency, potentially. I could put insta wires in. Might need to put insta wires in, because otherwise it's going to be 1.6 seconds of latency just to get from the top of the tower to the bottom, at least. Well, it doesn't necessarily have to be. I mean, it probably does necessarily have to be. Yeah, it would need to be, wouldn't it? So, it just needs a single insta wire, which can be arranged. But just today I'm going to be doing the logic of it, so I'm not going to do that. I'm just going to show you how the logic works today. So, um, on the on the layer above the layer below, what happens is so anyway. Oh God, my brain. Um, Sorry, my energy level has crashed. And they just started playing loud music over the road. It's like... just shut my window, but... So logically, actually, we need something like this. So there's a loop around the outside. So it goes something like that. Right, and then on this side it comes in here, and then there's a switch here. Um, and then going around the outside here. Switch there. And so what this means is that if this side is on up here, right, and this side is off, that will then switch this off here, right, and then the output at the bottom will be, it will be one on one on this side and 0 on this side, and what that will tell you is that this number here is larger than that number here. Right, so if you think about the first instance where there's a 1 in the binary number that doesn't match a 1 in the other binary number, will result in one of these sides being on and the other one being off. And what this system here does, it ensures that in that instance, well, firstly, right, it will do a stack of ones all the way up to that order of 2 in the 16-bit number. So it'll be 1, 1, 1. So if it's the 8th bit, it'll be 8 ones up to the 8th bit, right, on that side. And then, like, let's say there's a 1 in the other number that's not matched by a 1 in the first number, right? Then it'll be a stack of ones up to that number as well. So you'll have essentially 2 towers of ones next to each other. And what we want is for the higher tower to erase the smaller tower, and that will tell us which number is larger. Just by looking at the bottom and seeing which one outputs a 1 and a 0, because if it completely erases the shorter tower, then it'll output a 0 at the bottom, right? And what this mechanism here does is ensures that. So in this case, again, let's say it's this side that has a 1 that's not matched, so this is 1 and this is 0. This will come along here, that will be 0, so that switch will be open, so it will go down here, and it will switch off any ones that come in from this side, right? So it'll overwrite them all to 0. And obviously this side is irrelevant because it'll be switched off by this side, and also because that side will be 0 anyway, right? So that'll be switched off, so there'll be no overwriting there. So there'll be a 1 coming out the bottom here. Although that does mean I need to make I do need to make the system for the value there to propagate down as well. So I need to add a wire here going just straight down to there, basically. And of course, if they're both on, then the switch from here will turn that off, right? And then the switch here will turn this off, so there'll be no switching, right? And then it'll be 0 at the bottom, and that'll be the null case, which is that the two numbers are equal to each other. Basically, I need to stack these up. So I need a line that goes literally like that. And then I need a line that goes like that. Except hang on, that doesn't work because that's the off switch, so that's wrong. Sorry. Because that feeds into the off switch there, so I want one that feeds into the on part. So I think I'm actually have to make this tower a lot larger than you'd think it would be, this little bit at the back here, because A, it makes it simpler, and B, it means I can fit insta repeaters in, because otherwise, because essentially anything about this stack of 16 numbers is going to be done in series rather than in parallel, which means that for every non-instant repeater I put in, that's 0.1 seconds of delay. Is there a faster way I can do this? I believe there is actually, in a way which would be entirely in parallel. Or at least to all intents and purposes in parallel. All I actually need to do is identify the point where one of the towers is large. So let's say, let's go back to the stacks of ones, right? I need to just identify where the first gap is, so I can just put a check in that checks if there's a gap there. And if there's a gap there, it will return true or false, right? I can get rid of this actually. This is probably a very silly way of doing it. Stick with that first bit. Sorry about this, but these guys are so annoying. They make a very, very annoying noise, so yeah. Gotta get rid of him. This is the reason Minecraft was censored in China. So all I need is a return line from the next layer up. It's literally going to be the same again, basically, but with the return line from the next layer up. So just repeat that circuit there. And the difference is, so basically, this basically just converts the number from a number format to a format of a stack of ones up to the highest power of 2 that's not the same across both numbers. So like that, and then in the middle, hang on, does it need to be AND gated before that? Yes, it does. No, it doesn't. No, it does not. I'm just going to cut these out because I want this to be gaps in the structure when I copy and paste it. But, yes. Hmm. This design does still require Insta wires, is the problem. So anyway, first things first, another AND gate. No, there's not much joy to be had in that setup. Okay. More joy to be had in this setup, to be honest. And that's the output on that side. That's the output on that side. Basically that's just on the one instance where one side is on, like there's going to be a... So in the instances where one side is on and the other side is off, right, which will occur only on which, only if one of the numbers is larger than the other, right, it will return a 1 on the side where the number is larger than the other. Basically I need to stack out the back here to sum up all these signals. And I will need some insta repeaters on the side here. To propagate the signals down instantly, basically. So basically I need to adjust this here to be compatible with InstaWire. Which I think the best way to do that is to go like this, and then I have the Insta repeater essentially here. And stagger it all the way up, basically. So if I put an Insta repeater there, that comes around there. Oh god, my head. So I can put it, basically I can put it there versus there. But just for the sake of argument, it's probably not going to work, is it? It's probably going to go far too far. So it's 4, so it's there. How far does that signal propagate? If I turn that off, that signal propagates all the way out, as expected, as it should. Except no, it doesn't, because it doesn't quite get back to itself. Right. What the signal needs to do is get around to the next repeater on the next layer down, right? Which is that repeater there. And as you can see, it doesn't quite make it. It's interesting, I'm surprised that's 16 blocks. Guess if I get rid of that, it does still not quite. I know it makes it now. So that works. But that's going to be, so you can see the basic layout now, basically. Convert each number into a stack of ones from its leading unique bit, and then figure out which number has the first leading unique bit, and then that'll tell you which one's larger. So this circuit here compares each bit and see if it's unique or not, and this circuit here converts it into the stack, and then compares the stack to see if there's which one, to see if they're both the same at that point. But thanks for watching, and good night.